So it's great pleasure to have Yoav Zimhony, who will be telling about commutative control data for smoothly locally trivial stratified spaces.
Okay, thank you for the invitation. It's very nice to be here. So I'm going to talk about this thing. We will define everything. Let's begin. So we will start with a bit of background and how we got to this motivating question, and then we will describe the proof strategy and various steps in the proof of this motivating question. Okay, so the background is Hamiltonian G-spaces. We have a compact Lie group, the Lie algebra and its dual, and we have a symplectic manifold, and the group act symplectically on the manifold in a Hamiltonian fashion. So we have a momentum map like before. Here we don't require the group to be abelian. Okay, so let's recall the definition of deformation retractions. Given a subset of a topological space, a deformation retraction from the space to the subspace is a homotopy from the identity on A to some map which sends all of A onto C. And we say that this deformation retraction is strong if at all times it is the identity on the subspace. And we say that it is weak if we allow the subspace to move within itself. Okay? So now we can describe the motivating question. So let's fix a G invariant inner product on the dual of the Lie algebra with some norm. And we have two interesting subsets. First is the zero level set of the momentum map. And the second one is the critical set of the norm squared momentum map. And this will be a subset of the critical set, many times even a connected component. So the motivating question is the following. For each of these subsets, is there a G invariant neighborhood of it and a G equivariant smooth weak deformation retraction from this neighborhood onto the subset? Now let's talk a little bit about this smooth weak bold text. Why can't we demand the deformation retraction to be strong? So for submanifolds, when these subsets are submanifold, strong deformation retractions follow from the tubular neighborhood theorem. We just take the multiplication by scalars. But when they are not manifolds, then we cannot expect to obtain strong retraction, because smooth, strong retractions by the constant rank theorem, their image must be a manifold. And here you have an example when these subsets are not manifold. So we can only expect, if we want smoothness, we can only expect our deformation retraction to be weak. Okay. So let's talk a little bit about the literature of this around this question. It was conjectured by Harada and Karshon in their 2012 paper. They had a certain localization theorem for Dusterman-Heckman distributions, and they had general localizing set for these theorems, but they needed these technical assumptions that their localizing sets admit such a smooth weak deformation retraction, G equivariant, yada yada. And what we show is that they do not need these extra assumptions. For the critical set, you always get these technical assumptions. If we do not require smoothness, if we are only interested in continuous deformation retractions, then this is already known. And both Lerman and Woodward have a proof attributed to Dustermat, and they show it specifically for these subsets. And also, if you know that these subsets are stratified, and we are going to talk about it soon, then you can also use the general results of Goretzky, Flau, and Wilkin, and apply it to the stratified structure of these subsets. But again, all of these results are only continuous. Okay, so let's talk about stratified spaces, because we are also going to use stuff. Our constructions are going to be very similar to stuff that Goretzky did, but we are going to do everything smoothly. So what is a stratified space? Given a manifold, and we have some closed subset of it, a stratification of this subset is a composition of it into disjoint union of manifolds. Okay, these are called strata, and the single one is called stratum. And we wanted the composition to be locally finite. So each point has a neighborhood which only sees a finite number of strata. And there are other conditions which control how strata behave next to each other. And we are not going to talk about it right now, because we are going to present a a stronger condition which we will use. Okay, so I will not talk about the frontier condition and Whitney B. So some example of stratified spaces, embedded submanifold. These are just stratified to one stratum. The union of the x's in the plane can be stratified. You take the origin and the 4 rays. Also, a result of Whitney shows that every real algebraic variety embedded in some Rn can be Whitney B stratified. And the last 2 examples are really what is interesting for us, is that the orbit type stratification of a manifold with an action of a compact Lie group can be stratified. And when you take this stratification and you intersect the strata with this closed subset, you get a stratification of these closed subsets. Okay, note that this is not always the case, that when you intersect some stratification of a manifold with a closed subset, you get a stratification. This is quite a special case. Okay. Okay, so we want to prove our this motivating question. And what is our strategy to prove it? So first, we are going to show that this subset, when stratified by orbit type, they satisfy a strong stratified regularity condition. And we will exactly describe what we mean by this. But this is much stronger than Whitney B, for example. Okay. Secondly, we are going to use this local condition on these stratified spaces to construct a collection of tubular neighborhood of strata. So each stratum will have a tubular neighborhood. And these tubular neighborhoods are going to work together in a suitable sense. They're going to commute in a suitable sense that we will define. And finally, and I don't think we will be able to get to this last part today, given such a collection of tubular neighborhood which commute, you can quite easily construct this this weak deformation retraction. But what we're going to do is we are going to show this definition, talk a little bit about how you can construct such a collection, and you can believe me that you can do the last part. Okay. So let's give our definition of the strong stratified local regularity condition. So we have our stratified subset. Given a stratum of dimension k, so this is one of the submanifolds, and a point in this stratum, we say that the stratified space is smoothly locally trivial with conical fibers around this point. If there's a neighborhood of this point in M, and a stratified subset of Rn minus k, k is the dimension of this manifold, with conical strata. Conical means that the multiplication by scalars in Rn minus k preserves the strata, and a diffeomorphism from this neighborhood to this, which sends our stratified subset to a set of the form Rk times this stratified subset of Rn minus k, such that its strata from our original stratified subset is identified with the strata of this form, Rk times some strata of the stratified subsets in Rn minus k. And instead of looking very hard at this, let's look at an example of a locally trivial stratified space. So we have this space. We have one-dimensional strata, the green line. We have 4 two-dimensional strata. These are the blue surfaces. And we have two three-dimensional strata, the red parts. And you can describe this stratified subspace by R1 times this picture. So the smooth local triviality means that there is a diffeomorphism between these. And the conical fibers mean that in this picture, all the strata are conical. Okay, this is clear? Okay. Let's give some non-examples before we move to the examples. So I said before that every real algebraic variety can be Whitney B stratified. So this is not the case that they are smoothly local trivial with conical fibers. For example, the 0 set of this function, it is smoothly local trivial around 0 when you stratify it like this, but the fibers cannot be conical because these 2 strata come from the same angle. And this is an example of Whitney that you cannot even expect smooth local triviality from general stratified spaces. So I will not describe this exactly, but you can believe me that this cannot be smoothly locally trivialized. Okay, and the reason is this curly surface in here, and these three surfaces. Okay, so the examples. The following stratified subsets are smoothly locally trivial with conical fibers. The first is that the orbit type stratification of a manifold with an action of a compact Lie group is smoothly locally trivial with conical fibers. And secondly, the stratification of our interesting subset is also smoothly locally trivial with conical fibers. So we have what we want for this, and we can just continue working with the general stratified subsets which have this property. And the proofs of these examples, they use the local normal form theorem by Gilman-Sternberg and the Koszul-Slice theorem for the first one, which is to be expected because smooth local triviality with conical fiber is a local property. Okay. Any questions about smooth local triviality, conical fibers? Okay. So to present the control data that we are going to build, let's first recall the notion of a tubular neighborhood. Given we have a submanifold, we have the notion of a normal bundle, which is defined like this. This is a vector bundle over X. And the tubular neighborhood theorem says that we can embed the normal bundle inside the manifold in a way which identifies the zero section with X. So what do you mean by a collection of tubular neighborhoods? For a stratified subset with strata indexed by X, a collection of tubular neighborhoods is the following data. We have Tx, this is an open subset inside M, and this is the image of the tubular neighborhood embedding. Okay, this is a neighborhood of X. We have the multiplication by scalars coming from the normal bundle. In the normal bundle, we have multiplication by scalars. So we can also have multiplication by scalars in the image of the tubular neighborhood. And finally, we have some smooth distance squared functions, and we want them to be homogeneous with respect to these multiplication by scalars. Okay, so this is what we mean by collection of tubular neighborhood. For each strata, for each stratum, we have a tubular neighborhood of it. And our main theorem is the construction of a collection of tubular neighborhoods which commute in a suitable sense. So let's see the stratified subset, which is smoothly locally trivial with conical fibers. For example, one of our interesting subsets. Then there exists a collection of tubular neighborhood satisfying in the invariant definition the following properties. And before I will talk about each property, I will want to show you an example of what we want from such tubular neighborhoods. So let's talk about an example and then come back to this slide. Okay, so we are going to construct something for the union of the x's in the plane. And our stratification is we have the origin and we have the four rays. Okay, this is our stratification. Let's start by constructing a tubular neighborhood for the origin. So we'll just take for example, the unit disk, and we'll take the regular multiplication by scalars in the plane. And why this is good for us? Because the regular multiplication by scalars, it preserves the rays. Okay, for t bigger than 0, it preserves the rays. So this is one thing that we want. We want the multiplication by scalars of some strata of some stratum to preserve all the higher strata. Okay, so we built, and we also get a distance squared function. We can just take the distance squared function in the plane, normalized so that it is infinity in here. And now we want to construct a tubular neighborhood for this ray called Y. So one thing that we want is that the multiplication by scalars in Y, okay, so this is the multiplication by scalar, it needs to be tangent to level sets of the distance function of X. So the distance function of X is these blue lines. So the multiplication by scalars in Y needs to be tangent to those. So this is one restriction that we have. So it cannot be, so the naive thing would be just to take multiplying the Y factor, but this is not possible here. So we need this curly multiplication by scalars. The second thing that we want is that we want the multiplication by scalars in the tubular neighborhood of Y to commute with the multiplication by scalars of the tubular neighborhood of X. Here to commute with the multiplication by scalars in the plane. Okay? So this is another restriction that we want. And lastly, we also need a distance function from Y. And we want to construct it such that the multiplication by scalars of X, so the flow going like this, will be tangent to this to the level sets of the distance functions. So the distance function must look like these yellow lines. Okay, and one can show that the structure that we build needs to look like this. So now, after looking at an example, let's look at the general requirements. So we have a collection of tubular neighborhoods, and we want that the multiplication by scalars of Y to be tangent to level sets of the distance function of X for different strata. Secondly, we want the multiplication by scalars of Y to be tangent to level sets of the projection to X. Note that the multiplication by 0 is the projection to X in the tubular neighborhood. These two properties are part of Mother's original control data. And this is why this is called the control data for stratified spaces. These two properties are not part of the Mother's control data. First is the tangential. We want the multiplication by scalars of strata to reserve higher strata. Okay? And secondly, the commutative property. We want these maps to commute only when it is well-defined. Okay, this is not always well-defined, but when it is, we wanted them to commute. Okay, any questions about this? About the structure we build? Okay, so you can believe me that given such a structure, you can construct your smooth weak deformation retraction. Let me show you just what we say. You can construct a smooth weak deformation retraction from this subset given by the close, the places where the distance function is less than 1 to your stratified subset. And now let me talk about a nice technical tool that we use in order to construct such control data. And this is Euler-like vector fields. So in here, what we try to build is we try to build a tubular neighborhood with certain conditions on the multiplication by scalars. So what I'm going to say is that Euler-like vector fields are a very useful tool when you try to do stuff like that. And let's present them. Okay, so first, the Euler vector field in Rn is just this vector field. This is the identity vector field. And the flow of this vector field is the multiplication by exponent t in Rn. Now you can also define the Euler vector field in vector bundles. This should be the Euler vector field in each fiber. The vector field whose flow is the multiplication by exponent t in the bundle. Now Borsten, Lima, and Meinrecken defined Euler-like vector fields along submanifold. So given we have a manifold and we have a submanifold, there's a notion of Euler-like vector field along a submanifold. This is a vector field on M, similarly to how in vector bundle, the Euler vector field is a vector field on the vector bundle. And the linearization of this vector field needs to be the Euler vector field in the normal bundle. Okay, so these are certain kinds of vector fields on M. And here we will also require them to be complete. So we need to think about them being complete, what we build. Okay, so what are the properties of these vector fields and why they help us construct this control data structure? So two very nice properties of Euler-like vector fields is that given an Euler-like vector field along X, you can obtain a tubular neighborhood and the multiplication by scalars, such that the flow of the vector fields becomes the multiplication by exponent t. Okay, so we said that Euler vector field, the linearization of it needs to be exactly the Euler vector field, but also in the manifold, when you take the flow, this is exactly the same. Okay, And the second nice property is that being Euler-like is a local property. So given a point in your submanifold, you can check whether a given vector field is Euler-like locally. And it is preserved under smooth convex combination. So given some Euler-like vector fields defined in neighborhoods of points, you can patch them together using partitions of unity. And what this lets you do is that you can patch together local tubular neighborhoods to a global one, while also retaining information regarding the multiplication by scalars, because the multiplication by scalars is given by the flow of your vector, if the vector field that you constructed. And finally, they allow for the following translation. So before we talked in the language of tubular neighborhoods and multiplication by scalars, and we are going to translate it to the language of Euler-like vector fields. So instead of requiring some multiplication by scalar to preserve a submanifold, we can require the Euler-like vector field to be tangent to it. Instead of requiring the multiplication by scalars to be tangent to level set, you can require the Euler-like vector field to have the lead derivative of this function by the Euler-like vector field to be 0. And instead of requiring your flows to commute, the multiplication by scalars, you can require that the Euler-like vector fields commute. And then you can do many, many things locally and patch them together in a suitable sense and get the structures that you want. That's it, I think. Any questions?
Perfect. Let's thank Yoav, first of all. Thank you for a very nice talk. Yeah, any quick questions for Yoav?
Do you anticipate other applications for these Euler-like vector fields, other types of applications?
So in the papers of Borstein, Lima, and Meinrich, they show a couple of nice theorems using these vector fields, mostly like local normal form theorems and stuff like that. It's a nice read.
Thank you.
Thank you.
Thank you. Let's thank you all again.